on orthogonal operators. We have learned definition and defining properties for unitary and orthogonal operators. They are in fact norm-preserving. Now we will focus on orthogonal operators in the Euclidean space and understand the geometry of these operators. We will first start with rigid motions. Let V denote a finite dimensional real inner product space. Definition: a function t from V to V is said to be a rigid motion if norm of Tx minus Ty is equal to norm of x minus y for every x and y in V. The function t is not necessarily a linear function, that is what is to be noted here. It is just a function on a finite dimensional real inner product space. And as you can see that the distance is being preserved. Example: orthogonal operators on finite dimensional real inner product spaces are rigid motions. And the function denoted by t suffix a from V to V given by T a of x is equal to x plus a for a fixed a in V is called the translation function on V. You can see that it is a rigid motion, but not a linear map if A is a non-zero vector. Theorem: let V denote a finite dimensional real inner product space. Let T from V to V be a rigid motion. There exists a unique orthogonal operator P and a translation Ta on V for a unique A in V such that T is equal to Ta composition P. So, this theorem in fact characterizes rigid motions on finite dimensional real inner product spaces. Proof: let P from V to V be defined by P of x is equal to T of x minus T of 0. If we can show that P is orthogonal, then we have proved that T is equal to T of T0 composition P. And what is T of T0? That means the translation map from V to V, and it is translating by T0. Moreover, if A and B belong to V be such that Tx is equal to P1x plus A is equal to P2x plus B, then by taking x is equal to the 0 vector, it follows that A is equal to B. Why is that so? Because P1 and P2 being linear maps, we have P1 0 is equal to P2 0 is equal to 0, and therefore A is equal to B. Also we get P1x is equal to P2x for all x in V, and therefore P1 is equal to P2. This shows the uniqueness of the expression. Now for x in V, norm of Px square is equal to norm square of Tx minus T0, and that is the same as norm square of x minus 0, that is because T is a rigid motion, which is the same as norm of x square, and therefore norm of Px is equal to norm of x. And for xy in V, norm of Px minus Py square is equal to norm of Px square minus 2 times inner product Px Py plus norm of Py square. We have showed just now that norm of Px is norm of x. Therefore, this expression on the right hand side is equal to norm of x square minus 2 times inner product Px Py plus norm of y square, and norm of x minus y square is equal to norm of x square minus 2 times inner product xy plus norm of y square. Therefore, using the equality norm of Px minus Py square is equal to norm of Tx minus Ty square is equal to norm of x minus y square, we obtain inner product Px Py is inner product xy. We now show that P is a linear operator on V, and then we are done. Look at Z is equal to inner product square P of x plus Cy minus Px minus Cpy for vectors x and y and scalar c, which is the same as, after a rearrangement, norm square of P of x plus Cy minus Px minus Cpy, and therefore it is equal to norm square of P of x plus Cy minus Px plus c square norm of Py square minus twice c inner product P of x plus Cy minus Px comma Py, which is the same as norm of x plus Cy minus x square plus c square norm y square minus 2c times what you can see inside the bracket, that is inner product P of x plus Cy comma Py minus inner product Px Py, and that is c square norm y square plus c square norm y square minus twice c times inner product x plus Cy comma y minus inner product xy, and that is equal to 2c square norm of y square minus 2c times inner product xy plus c norm y square minus inner product xy, and that is equal to 0. Therefore, P is linear. This proves the theorem. It is easy to verify that composition of orthogonal operators are orthogonal. It follows that composition of rigid motions is a rigid motion. In fact, the collection of rigid motions form a group. We will study the action of the group of rigid motions of R2 on the conics and the orbits under this action when we study symmetric bilinear forms. Rigid motions on finite dimensional real inner product spaces are distance preserving maps, and we have proved that they are composition of translation and orthogonal operators. Not only that, we have seen that it is of the form T0 composition P, where P is an orthogonal operator and T suffix T0 denotes translation by the vector T0, where T is the rigid motion to begin with. Moreover, this expression is unique. Now, what is interesting is that if the rigid motion T fixes the 0 vector, that means if T0 is equal to 0, then what we get is that rigid motion is nothing but an orthogonal operator. So, a rigid motion on a finite dimensional real inner product space fixing the 0 vector, that means T0 is equal to 0, is nothing but an orthogonal operator. So, we see orthogonal operator once again from a different angle. Let us now see two very important orthogonal operators on R2, namely the rotation operator and the reflection operator. The rotation operator T theta on R2 is an orthogonal operator, and that we can see from its matrix representation given by cosine theta minus sine theta in the first row and sine theta cosine theta in the second row with respect to the standard basis of R2. Therefore, T theta maps the standard basis of R2 to an orthonormal basis. Therefore, it is orthogonal, and it follows that T theta preserves norms and orthogonality. But T theta has no real eigenvalue, so it cannot be self-adjoint. In fact, the operator T theta star is nothing but the rotation by an angle minus theta. We now generalize and define a rotation operator on an arbitrary finite dimensional real inner product space. The definition: let T be a linear operator on a finite dimensional real inner product space V. The operator T is called a rotation if either T is the identity operator or if there exists a two-dimensional subspace W of V and an orthonormal basis V1 V2 of W such that T V1 is equal to cosine theta V1 plus sine theta V2 and T V2 is equal to minus sine theta V1 plus cosine theta V2, and Tx is the 0 vector for every x in W perp. Then we say that T is a rotation of V about W perp, and the subspace W perp is called the axis of rotation. You can see that this is indeed an imitation of the usual rotation operator on R2, and it indeed generalizes, because if we see V is equal to R2, then this definition leads to the usual rotation operator T theta. Now, the reflection operator, let W be a one-dimensional subspace of R2 or a line in R2 passing through the origin. A linear operator T on R2 is called a reflection of R2 with respect to W. Tx is equal to x for every x in W, and Tx is equal to minus x for every x in W perp. The proposition: a reflection operator T on R2 is orthogonal. Choose a vector V1 in W and a vector V2 in W perp such that norm of V1 is equal to norm of V2 is equal to 1. Then this set V1 V2 is an orthonormal basis for R2. That is because they are orthogonal with norm 1. then we have by definition T of V1 is equal to V1 and T of V2 is equal to minus V2. Hence, T maps the orthonormal basis V1 V2 to the orthonormal basis V1 comma minus V2. Therefore, T is orthogonal. Let us understand the matrix representation for the reflection operator. Let theta be the angle from the positive x axis to the line W, and let V1 denote cosine alpha comma sine alpha and V2 denote minus sine alpha comma cosine alpha. Then this set B consisting of V1 V2 forms an orthonormal basis for R2. And since T of V1 is V1 and T of V2 is minus V2, we have the matrix representation of T with respect to this basis B as this 2 cross 2 matrix whose first row is 1 0 and the second row is 0 minus 1. Now let P denote this 2 cross 2 matrix whose first row is cosine alpha minus sine alpha and the second row is sine alpha cosine alpha. Then the matrix representation of T with respect to the standard basis B is equal to E1 E2 is this box T B, and that is equal to P times box T B times P inverse, where this second B is that basis consisting of V1 V2, and that is equal to the 2 cross 2 matrix whose first row is cosine 2 alpha sine 2 alpha and the second row is sine 2 alpha minus cosine 2 alpha. This therefore gives the matrix representation of the reflection operator with respect to the standard basis of R2. We now generalize and define a reflection operator on an arbitrary finite dimensional real inner product space. Definition: let T be a linear operator on a finite dimensional real inner product space V. The operator T on V is called a reflection if there exists a one dimensional subspace L of V such that T of x is equal to minus x for all x in L and T of x is equal to x for all x in L perp. We call T a reflection of V with respect to L perp. If L is the span of this vector V with norm V equal to 1, then T from V to V given by Tx is equal to x minus 2 times inner product x comma u is the reflection of V with respect to L perp. Now a theorem. Let T be an orthogonal operator on R2. Let A denote the matrix T B, where B is the standard basis for R2. Then exactly one of the following is true. The first one says that T is a rotation and determinant of A is 1, and the second one says that T is a reflection with respect to a line through the origin and determinant of A is minus 1. Proof: T is orthogonal, therefore set containing T1 T2 is also an orthonormal basis for R2. Now since Te1 is a unit vector, we have Te1 is equal to cosine theta comma sine theta for a unique theta which is greater than or equal to 0 and less than 2 pi. Now Te2 being orthogonal to Te1, we have either Te2 is equal to minus sine theta comma cosine theta or sine theta comma negative of cosine theta. Now it is very easy to verify that the first case, that is TE2 equal to minus sin theta comma cosine theta, gives a rotation, and the second case, that is TE2 equal to sin theta comma minus cosine theta, gives a reflection. Here you see diagrams which represent rotation and reflection in the real plane R2. If T1 and T2 are orthogonal operators on an inner product space V, then T1, T2 is also orthogonal, and that is easy to verify using definition. Moreover, if V is a two-dimensional real inner product space with orthonormal basis V1 comma V2, then we can construct an isomorphism T from V to R2 such that T of V1 is equal to E1 and T of V2 is equal to E2. Moreover, inner product Tx comma Ty is equal to inner product x comma y for every xy in V. We get the following classification from these observations. Theorem: let T be an orthogonal operator on a two-dimensional real inner product space V, then T is either a rotation or a reflection. Moreover, T is a rotation if and only if determinant of T is 1, and T is a reflection if and only if determinant of T is minus 1. And a corollary which says that let V be a two-dimensional real inner product space, the composite of a reflection and a rotation on V is a reflection on V, and that is because of the determinant condition. We have classified all orthogonal operators on the two-dimensional Euclidean space R2. We have seen that they are either reflection or rotation. We have also defined the concept of reflection and rotation in general on finite dimensional real inner product spaces. And what is interesting is that if we look at a two-dimensional real inner product space, that is structurally the same as the two-dimensional real Euclidean space R2. And we can naturally generalize and characterize all the orthogonal operators on two-dimensional real inner product spaces and see that they are also nothing but reflection and rotation, and not only that, they are also characterized in terms of determinant. So, if determinant is 1, then it is the rotation operator, and if determinant is minus 1, then it is the reflection operator.